Hi, I'm Angela Potochnik. I'm a professor of philosophy at the University of Cincinnati in the United States, and I'm also the director of the University of Cincinnati's Center for Public Engagement with Science. I'm really excited to participate in this interesting interdisciplinary event. Thank you to the organizers for including me. I look forward to the in-person sessions, or rather the live sessions later in the month. And in the meantime, here is my short talk with what I hope can be a contribution to this discussion. As I mulled over what I might be able to say that would be of interest to this group, I settled on a somewhat negative theme, what not to expect from theories. This is because, in my view, some amount of confusion and needless disagreement has arisen in a variety of different scientific fields by anticipating that some successful theories can do more than they actually can, and also by holding other theories to too high of a standard. So that's the focus of my talk, what not to expect from theories. I'm going to raise three interrelated ideas about scientific accounts, including scientific theories. First, that scientific accounts are highly specific to their aims. Second, that the standards by which theories and other accounts should be judged vary. And third, that integration is the exception rather than the rule for accounts and specifically theories in science. All of these ideas are influenced by my interests and the ideas that I've developed as a philosopher of science, especially in my 2017 book, Idealization and the Aims of Science. I'm not going to be able to fully motivate these ideas in this brief talk, but I do hope to spur your thoughts and to convince you to look for resources on these topics in philosophy of science. All right, so getting started. The first point that I wanted to make, as I said, or the first task that I want to accomplish is to motivate the idea that scientific accounts are highly specific to their aims. So I keep going back and forth between accounts and theories and what I've said so far. So to make this explicit, I mean to use the term accounts as a kind of umbrella term to include not just theories, but also scientific models, laws, and other forms of theoretical achievement in science. All right, so let's start here. What is responsible for the scarlet ibis's coloration? Why is the scarlet ibis so bright? If this talk were occurring live, I'd ask you to generate a list of likely causes. But since this is recorded, instead, I'll just gesture in the direction of some different kinds of causes. There's something we can say first about scarlet ibis physiology, namely that it produces feathers with carotenoid pigmentation. We also might detail the specific carotenoid carrier protein in the blood of scarlet ibises, but that's lacking from white ibises. Considering in turn evolutionary influences, there's something to say about why this species of birds evolved to have feathers of this color. Indeed, there's something to say about the role of selection, such as this coloration's role in mate attraction. And also there's something to say about which gene complexes support the necessary enzymes and selective transport of carotenoids, how this evolved in birds. Considering in turn environmental influences, we could note the presence of dietary carotenoids in the scarlet ibis's environment. The coloration wouldn't be possible without those carotenoids being available. And we can also talk perhaps about how parasite load influences carotenoid metabolism and transport. Nor is this list the end of it, the end of the list of what is responsible for the scarlet ibis's coloration. I haven't yet mentioned developmental processes, behavioral traits, any role for phenotypic plasticity, and more. All of these are at least in part responsible for the ibis's feather color. Our world is a complicated place. In particular, there's what I like to call causal complexity. Any event, in biological systems or not, has innumerable causes, processes stretching arbitrarily far back in time. Moreover, these causes interact. There is causal feedback and other complex relationships among them. There's nothing special about this example of the scarlet ibis's coloration. Literally anything would work to illustrate this point. When any of us ask what is responsible for some phenomenon of interest in science, if we sort of look in every direction that we might, we'll come up with a long list of directions that scientific research could go in. Science has developed many techniques for accommodating causal complexity. Some approaches, like dynamical systems theory, apply abstract mathematical formulations to summarize the behavior of statistical aggregates. Other approaches attempt to accurately portray the influence of one cause or set of causes, abstracting and idealizing away from other influences. Still other approaches attempt to reflect the interplay of several causes with the aim of providing a nuanced account of the phenomenon in question. Each of these techniques is a way to focus in on one causal pattern, as I think of it. That is, how the influence of one or possibly more focal causes tends to play out in a complex phenomenon, while ignoring, setting to the side, at least for present purposes of some particular research program, other causal patterns that are embodied in the phenomenon. Consider again all the kinds of influences on scarlet ibis coloration. If the aim of scientific investigation were simply to characterize the causes, this would motivate an exhaustive story of the highly specific combination of influences that happen to bear on this phenomenon. But this isn't what usually happens. Rather, a biologist comes to her investigation of the scarlet ibis or any other organism with specific interests. They are interested in the evolution of carotenoid metabolism and selective transport in birds in general, or perhaps whether and in what ways sexual selection is responsible for carotenoid coloration, or how parasite load influences carotenoid metabolism and selective transport, or so on. This list can be as long as our list of possible influences that we walked through on the last slide. So I would characterize this as a question of which causal pattern this biologist in particular is interested in. Causal patterns may be more general, like carotenoid metabolism in birds, or more nuanced, like how several of these causal factors combine for the scarlet ibis in particular. Each of the research projects targeting the scarlet ibis that I've gestured toward thus has a more specific aim than accounting for the scarlet ibis's coloration. The aims vary from targeting this as an instance of the evolution of carotenoid metabolism, to this as an instance of sexual selection, or to this as an instance of parasite load affecting morphology. All right, that's the quick first point, or first idea at least, that I wanted to raise, if not fully defend. Second idea is that in light of scientific accounts being tailored to highly specific aims in this way, the standard by which those accounts should be judged vary. So on the view that I've already sketched, research priorities determine the specific aim of the investigation and thus shape what causal information is relevant. And if I'm right that causal patterns are the aim, then causal information that is not relevant to the immediate research interests, either directly or indirectly relevant, is not only not needed, but it's even contraindicated. That extra causal information shouldn't be included in the account, in my view. This idea, I think, is simple when you put it in terms of an example. So going back to our scarlet ibis. If a researcher investigates scarlet ibis coloration as an instance of sexual selection, then she will not immediately investigate parasite load. That's not the aim. Parasite load is not directly relevant to how the scarlet ibis's coloration factors into mate selection, and it will be ignored. There is, though, notice an exception to this if it turns out that parasite load seems to affect coloration, such that coloration plays a role in mate selection as an indicator of health. Then, if this were the case, parasite load would emerge as indirectly relevant to the research priorities, even though not directly targeted. So scientists on this view aren't sort of necessarily entirely setting the agenda of what sort of causal factors should be discussed, but they are narrowing the agenda such that only causal factors directly or indirectly to the causal pattern of interest are relevant. Many other causal influences, such as developmental pathways, phenotypic plasticity, and more, remain irrelevant to the research, even though these are causally relevant to the phenomenon of the scarlet ibis's coloration. It follows from this that when a phenomenon of interest is of interest to different research programs, there are multiple accounts of the same phenomenon, each one focusing on a different causal pattern and ignoring features that are incidental to those specific interests. Because of this, I think it sometimes happens that scientists take themselves to disagree when actually their accounts are just after different things. I motivated this idea for biology in a bioscience paper from several years back. This is from 2013, And then much more recently, with a paper co-authored by my former graduate student, Guy Sanchez de Oliveira, motivated this for the cognitive sciences in particular, in a paper in topics in cognitive sciences. I suspect that differences in theoretical commitments across a scientific field arise more often from differences in research aims than from any true rifts in theories or different commitments to facts about what's going on in the phenomena. Okay, this lightning speed through quickly raising ideas. I'll move on to my third and last idea that I'll note in this talk. In particular, I want to suggest that integration of these separate accounts that respond to specific aims is the exception in science rather than the rule. Recall our long list of kinds of influences on the scarlet ibis's bright color. Each of these is the subject of actual scientific research. One view of science would suggest that scientific accounts of each of these causal patterns involved in scarlet ibis coloration provides one part of the story, and that the accounts can be slowly integrated to provide more and more of the complete story over time. That's a view of integration. In contrast to that picture, I think that each of these accounts casts light on a different range of related phenomena. To choose 3 of the accounts in our running example, these separately cast light on avian coloration in general, on the scarlet ibis's particular metabolism, and on the role of bright coloration in sexual selection. So avian pigmentation and bright coloration in sexual selection are similar to my prior causal pattern perspectives that I pulled out earlier in the talk, whereas now I'm focusing in on scarlet ibis's particular metabolism, carotenoid metabolism, rather than parasite load. So that's a shift in account. I just wanted to flag that change. There are then principled reasons, I think, for keeping these separate accounts separate. Each account is only partly accurate of the phenomenon, capturing the part of the story that's of interest given the specific research program at hand, and neglecting or possibly even misrepresenting, using idealizations, other parts of the story to accommodate that specific focus. There are important advantages to providing these separate accounts. For example, this makes available mathematical modeling techniques that would be otherwise impossible. But perhaps most importantly, providing just one of these separate accounts and another in turn versus trying to integrate them into a single account enables each account of the scarlet ibis's coloration to be related to a range of similar phenomena that embody one causal pattern relevant to this phenomenon while deviating from others. So for example, if we're interested in the scarlet ibis's coloration as an instance of avian pigmentation in general, then it overly restricts that account to add in irrelevant to that general focus details about carotenoid metabolism in the ibis in particular, etc. Okay, I think that this is an important scientific advantage to resisting the integration of separate accounts of any given phenomenon. And I ultimately think that this ability of separate accounts to indicate a causal pattern that's embodied in a range of different related phenomena, such as avian pigmentation and the role of carotenoid pigmentation in avian pigmentation in general, that sort of role of our scientific accounts motivates the continued use of distinct accounts versus their integration into a single account of scarlet ibis coloration. Okay, so to summarize, here's what I've gotten up to in this talk. In other words, here's what not to expect from our theories and our other scientific accounts. First, we shouldn't expect general applicability. Any account of a phenomenon will invariably be partial and specific to its highly specific aims, in my view. Second, we shouldn't expect completeness. Such an account will get some features wrong or neglect them in light of its specific aims. There may well be multiple accounts that achieve different goals. And third, we should not expect from our theories integration. There are practical and principled reasons, I think, to maintain separate accounts that pick up on different features, different causal patterns in a phenomenon of interest. Sometimes research interests will motivate integrated accounts, but these will not replace the separate accounts but simply be added alongside them to our broader store of scientific knowledge. All right, thank you for listening. And as I said, I look forward to engaging with everyone at the end of June.